Okay, the first thing we're going to do is talk about where these infinite polynomials that I introduced about a month ago, more than that now, where they come from. The terminology for these they're called Taylor series. They're power series, meaning that they are series involving powers of x. And they go back as far as calculus goes. This is the way that Isaac Newton thought about functions when he was writing down his version of the calculus. So these go way, way, way back. So the way that we build these is we can build one for any elementary function. So all the buttons on your calculator, e to the x, log of x, sine of x, all those guys. As long as the function you have has the it's possible to take as many derivatives as you want. At some point, we will be able to build one of these things that we call a Taylor series. In section 9.1 of our book, they introduced this by first talking about Taylor polynomials. So this would be the infinite polynomials we were talking about in class if we were to cut them off at a certain point. So when we talk about the nth degree Taylor polynomial, we mean to just chop off that infinite polynomial we were thinking of before, and just chopping it off at the term that would have an x to the n in it. And so the formula that you see in front of you is how these are built. And the main thing is these numbers that are in front of each of these terms is coming from a derivative evaluated at some particular center point and then divided by a factorial. So anytime we build one of these polynomials, it's going to have a center, a number that we give it where the approximation is going to be centered, and then everything we build is going to be based on that. So I'll just do a couple of examples, but the main thing you'll want to make sure you understand the notation for here is when we write this superscript in parentheses like this, we're talking about taking the nth derivative. So another way of writing, instead of writing f double prime of a, you could write f with a raised 2 of a, and those are both ways of denoting the second derivative. That's important so we don't have to try to make up a notation for what it means to have, 11 tick marks or whatever would be the other notation. The other thing is don't forget your factorials. The weird one is 0 factorial, that's 1. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. And so on. So if you've forgotten what factorial means, just open a browser and Google what is a factorial. So those numbers we'll need to know to use this formula. Okay, so let's get started with an example. We're going to build the Taylor polynomial of degree 3 for the e to the x function. And again, this means basically building the infinite polynomial, but chopping it off when we get to the x cubed term. To do this, I have a table here, and what I'm going to put in the table are the formulas for the derivatives. I'm going to do that first. So for e to the x, it's sort of stupid. The first derivative is e to the x. The second derivative is e to the x. This number here is which derivative I'm taking. So the third derivative, also e to the x. So e to the x is not very exciting. And then in the next row of the table, I'm evaluating the derivative at the center point. So here the center is at a. So here I'm talking about the nth derivative evaluated at 0. So plugging in 0 into, if for x or e to the x, it gives me 1 in each case. Oh, I did forget to say, we think of the original function as the 0th derivative. So the original function, f of x, would be what we would consider the 0th derivative. So we haven't taken a derivative at all, is what we mean by that. Oops, I meant a there. Okay, so if I follow the formula for the Taylor polynomial, I have 1 over 0 factorial plus 1 over 1 factorial times x minus a, which is 0, to the first, plus 1 over 2 factorial x minus 0 squared plus 1 over 3 factorial x minus 0 cubed. So notice that the number that's here, the numbers in the table are the numerators in these fractions. Everything else is determined by, everything else is determined. So the table is only giving us the numerator of those fractions. In this case, this can be simplified a lot. Notice that if I'm centered at a, then saying x minus 0 is silly. That's just x. And so in this case, this polynomial is 1 plus x plus 1/2 x squared plus 1/6 x cubed. So the third degree Taylor polynomial for e to the x looks like that. You might want to pause the video and see if you can fill in the values for this one if you want to, and then start it again and I'll run through it. So here, again, the first thing I'm doing is calculating my derivatives as formulas. And so the first derivative of cosine is negative sine. The derivative of that is negative cosine. The derivative of that is positive sine. And the derivative of that is positive cosine. So we have to make sure we're keeping straight the positiveness or negativeness, but we can take derivatives as far as we want, starting with cosine, without much trouble. Once again, we're centering at a equals 0. So here, when I'm talking about the nth derivative at a, I'm talking about the nth derivative at 0. So that means I'm plugging 0 in for x into the formulas I have in the second row. So cosine of 0 is 1, negative sine of 0 is 0, negative cosine of 0 is negative 1, sine of 0 is 0, and cosine of 0 is 1. So those become my coefficients in my Taylor polynomial. Again, the number here becomes the numerator. So I have each term like that. And again, the numbers in the numerators here are the table values and nothing else. I don't need anything except for that last row from my table. Notice that these are polynomials, so I won't have sines and cosines in the actual p that I'm building. They should be a polynomial. So we don't use that second row for anything other than figuring out the third row in that table. Once again, this can be simplified a lot. This is 1. Every term that has a 0 in its coefficient is just really not there. So I'll have 1 minus 1/2 x squared plus 1 over 24 x to the 4th. The x to the first term and the x cubed term both have coefficients 0. So this is the 4th degree polynomial for the cosine function centered at 0. All right, one more. Again, you might want to pause the video to see if you can do it. But remember, the second row is just taking the derivative formulas. The third row is evaluating those. Notice here that there is a difference, that my center here is, my a is equal to 1. So here I'm evaluating my derivatives at 1 and not at 0. So the first derivative of 1 over x is negative 1 over x squared. And the second derivative would be the derivative of that, which would be positive 2 over x cubed. Here I'm just using the power rule. I'm thinking of my function, my original function as being x to the negative 1 power, and then just using the power rule. Each of those gets evaluated at 1. So when I plug 1 into the original formula, I get 1. When I plug 1 into the first derivative, I get negative 1. And when I plug 1 into the second derivative, I get 2. So the Taylor polynomial is going to be 1 over 0 factorial plus negative 1 over 1 factorial times x minus 1 to the first. So notice this is the first time we have not had x minus 0 in here. So, so I won't be able to do as much simplifying for this. Plus 2 over 2 factorial x minus 1 squared. I can simplify a little bit by admitting that I know what the factorials are. So that's 1. This is minus 1 times x minus 1 for the first. And this is plus 1 times x minus 1 squared. So in this case, the only thing I can really simplify is I can go ahead and evaluate these numbers to get the actual values, and then that's about all I can do. So you should try this. There's a second set of problems that I'll ask you to do and turn in. They're very similar to this, but try to practice going through the steps. Make sure you're taking the derivatives as derivative formulas as your first step, and then filling in the third row becomes just numbers in the next step. And see if you get can get the polynomials for the 3 problems on the next attachment.